The natural water cycle is often upset in urban areas. How can it be restored? Infiltration is one of the main processes at the basis of nature-based solutions for flood risk mitigation and water resources protection. In the cities, due to soil imperviousness is often limited, increasing runoffs, urban drainage system overload, and combined sewer overflow activation. Sustainable urban drainage systems include infiltration systems as integration tools of traditional sewer for runoff disposal at its source. Infiltration involves several benefits both for flood risk mitigation and water resource protection. The most relevant are runoff reduction, flow peaks limitation and lag, stormwater pollutant removal, base flow and groundwater recharge, pollution reduction of water bodies, money savings for costs related to urban drainage system and wastewater treatment plants. Moreover, they are simple, cost-effective, and easy to maintain. Infiltration systems' performance mainly depends on infiltration rate, that is, the soil permeability and groundwater depth. Depending on these parameters, different conditions can occur. Total infiltration, when the underlying soil is highly permeable, infiltration rates more than about 30 mm per hour. Total infiltration with storage, when a storage composed of high porosity materials or modular elements is added under the substrate layer. Infiltration rate lower than about 30 mm per hour or lower than rainfall intensity. Partial infiltration, also a drainage pipe is added to convey exceeding stormwater out of the system. For infiltration rates lower than 15 mm per hour or with tamping time of the storage more than 48 hours. A flow restrictor should be added if limitations on discharges into the downstream drainage system occur. Moreover, if the drain connection pit is far away, a double overflow must be considered. Infiltration systems also have some limits. They are not suitable to drain pollution hotspots and generally require larger flat area not also available. Moreover, infiltration system design need geotechnical investigations to confirm the infiltration suitability of the site. Effective upstream pretreatment is generally required to remove sediment and silt loads to prevent long-term clogging and subsequent failure of the system. In order to minimize the risk of groundwater rising into the infiltration system, ensure sufficient depth of the unsaturated material, and protect the groundwater from runoff contamination, a minimum distance of 1 meter between the base of the infiltration system and the maximum groundwater level should always be adopted. Moreover, the so-called first flush, generally the first 5 mm of rainfall, can be discharged into the drainage system to avoid the infiltration of the most polluted runoff component. To restore the storage capacity between consecutive rainfall events, infiltration system should be empty in 24-48 hours. The main infiltration systems are soakaways, infiltration trenches, and infiltration basins. Soakaways are excavations filled with a void material to allow the temporary storage of water before its infiltration to the ground. Small soakaways are constructed with geocellular units pre-wrapped in geotextile. Larger soakaways are composed of perforated precast concrete manhole rings surrounded with granular backfill almost 50 cm. They are generally connected in series and equipped with an overhead cementation well. Soakaways are generally sited underground. They do not benefit from pollutant removal through soil filtration, so they are best suited for runoff infiltration of small and low polluted areas. Infiltration trenches are simple linear soakaways. Their advantages over traditional soakaways are they can be kept shallower and help distribute the infiltration area, reducing the impact of less permeable soils. Infiltration basins are flat-bottom, shallow landscape depressions covered with vegetation or gravel. A layer of engineered soil mix of about 300 mm is usually considered to improve the soil durability. If compared to soakaways and infiltration trenches, infiltration basins require a large infiltration area, but benefit from pollutant removal through sedimentation, filter and absorption by vegetation and the substrate layer. Moreover, they have an aesthetic value and contribute to urban space requalification and biodiversity increase. Stormwaters are conveyed into the infiltration basin from the upstream catchment through an inlet pipe or channel. At its entrance, a flow spreader from erosion protection is usually installed. Side slopes should normally be no steeper than 1 to 3 for allowing vegetative stabilization, mowing, access, public safety and erosion prevention. Where temporary storage occurs, water level and rate should minimize the risk for site users and operators. Values of 20–30 cm are generally considered. Finally, the design of soakaways, infiltration trenches and infiltration basins should always guarantee an appropriate access to infiltration systems for maintenance and include monitoring.